Alright, so the last two topics that we're going to cover in this class are mathematical induction and binomial theorem. So first we're going to go over mathematical induction. There are two aspects to mathematics, discovery and proof, and they are of equal importance. So before we can prove things, we must discover them. So we cannot be certain of the truth of something that we discover until it's been proven. So in this section, we examine the relationship between these two key components, discovery and proof, of mathematics. So basically, we're going to go over one way of proving things, which is called mathematical induction. So let's try a simple experiment. Let's see if we add more and more of the odd number. So if I add, the first odd number is 1. If I added 1 to itself, not to itself, if I just add the first one, it's just 1. If I add the first two odd numbers, I get 4. If I add the first 3 odd numbers, I get 9. If I add the first 4 odd numbers, I get 16. If I add the first 5 odd numbers, I get 25. So I notice that when I add the odd numbers, I get 1, 4, 9, 16, and 25. And I can tell that on the right-hand side, these numbers are actually perfect square because I recognize that 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, and 25 is 5 squared, and 1 is just 1 squared. So when I do this, when I add the odd numbers, I kind of see a pattern going on, and then I'm going to make a conjecture that in general, when I add and odd numbers, the result is going to be a perfect square. So when I add 1, 2, 3, 4, 5, so when I add the first 5 odd numbers, I get that the result is 5 squared. So I can make a conjecture when I add the first 9 odd numbers, I get n squared. So I can't just check for 6, for 7, for 8. I can just check for a few of them and hold that this property holds, and then just say that that is true for everything. So a proof has to be a clear argument that demonstrates the truth of a statement beyond doubt, not just for a finite number of cases. So to prove, we must have a clear argument. So the proof technique that we're going to go over is called the principle of mathematical induction, which is basically saying that for each natural number n, if you have a statement about it, depending on n, you can show that the statement is true by doing these steps. So first, you got to show that the statement is true for n equals 1. So you got to show that. Then you can assume that for every natural number k, the statement is true for that k. So you're going to assume that it's true for k, so when n equals k, and then you're going to use that to show that it's true for the next step, for n equals k plus 1. So then if you can show that it holds for n equals 1, and if it's true for n equals k, then you can use that to show that it's true for n equals k plus 1. Then you have showed that the statement holds for all natural numbers n. You have proved that. So for example, to prove that for all natural numbers n, we have that 1 plus 3 plus 2n plus 1 equals n squared. So notice these are the first n odd numbers. So this is the problem that we kind of looked at, and we got an idea that it's equal to n squared. So when n equals 5, for example, in here, the first 5 odd numbers, this is given by 2n minus 1. This is how we represent an odd number. We take an even number and we subtract 1 from it, or add 1 from it, or subtract 3. So let's just check. When n equals 5, I would get 2 times 5 minus 1, which is 9, which is exactly the fifth one. So this is how I write an odd number, the nth odd number. So in order to prove this, so I made a conjecture by looking at the first 5 n's, and I saw that it's equal to the perfect square. But to actually prove it, we have to do it by induction. So we're going to do by induction, proof by induction. Show P of 1 is true. So I'm going to replace n equals 1 in both the left-hand side and the right-hand side, and I need to get a true statement. So for n equals 1, the left-hand side is going to be, when n equals 1, I'm going to have just the first term. 2 times 1 minus 1 is 1, so I'm just going to have 1 on the left-hand side, equals, what's the right-hand side? 1 squared. So the left-hand side equals the right-hand side because 1 equals 1. So P of 1 is true. Now we're going to assume that the statement holds for n equals k. So this is assumed to be true. So what is assumed to be true? It's assumed to be true that 1 plus 3 plus 5 plus 2k minus 1 equals k squared. So I can use this statement as true. But now the goal is to show that P of k plus 1 is true. So how am I going to do this? Well, I'm going to calculate P of k plus 1, the statement at n equals k plus 1, and somehow I got to use that this is true. So when n equals k plus 1, I'll get 1 plus 3 plus 5 plus 2k minus 1, that's for n equals k, and then one more, k plus 1, that's going to be 2 times k plus 1 minus 1. So this is when n equals 1, n equals 2, n equals 3, n equals k plus 1. So let's see what this equals to. So I'm not going to use that it's equal to k plus 1 squared. I need to use that somehow this, and then get to the conclusion, show that it's equal to k plus 1 squared. So what do you notice in here? What is 1 plus 3 plus 5 plus 2k minus 1 equal to? I can use this from here that it's equal to k squared. So then this is going to be equal to k squared plus 2 times k plus 1 is going to be 2k plus 2 minus 1, so plus 1. So this, I can factor this. This is k plus 1 times k plus 1, which is k plus 1 squared. So I have shown that P of k plus 1 is true because when I calculate this sum on the left-hand side for n equals k plus 1, I showed that it's equal to k plus 1 squared. By using this, I have replaced this sum with k squared, and then when I add it to this term, I get exactly what I need, k plus 1 squared. All right, so let's do another example. Prove using mathematical induction that for all natural numbers n, we have that this statement holds. So this is a geometric series, and it's actually a finite series. If you look at your notes, we have gone over this and just say that it's equal to that. Now let's prove that this is true. So to prove that this is true for any r not equal to 1, I need to first show that P of 1 is true. So on the left-hand side, what am I going to have? When n equals 1, I'm going to have just the first term, because n equals 1 is going to give me r to the 0, which is 1, and then a times 1, which is just a. So this tells me that on the left hand side I just have a. So this is the left hand side. And what am I going to have on the right hand side? On the right hand side I have a times r to the 1, because n is 1 over r minus 1. And this cancel, so I have that it's equal to a. So the statement is true for p of 1. So the second step is assume p of k is true. So when n equals k, I have a true statement. So I must have that a plus ar squared plus ar, instead of n, I'm going to have k minus 1 equals a times r to the k minus 1 over r minus 1. So I can take this as true. This is assumed to be true. And then I need to use this to show that p of k plus 1 is true. So I'm going to write p of k plus 1, the left hand side of it, and then I'm going to calculate it and hope to show that it is equal to that when n equals k plus 1. So I need to show that a plus ar plus ar to the n plus 1 minus 1 equals ar to, k. ar to the k plus 1 minus 1 over r minus 1. So this is what I need to show. So I'm going to start with the left hand side. A plus ar squared plus, I'm going to write the term before k plus 1. So the term before k plus 1 is ar to the k minus 1, and then plus this one. K plus 1 minus 1 is just r to the k. Okay, so I'm going to calculate what this is. And I'm hoping to show that it's equal to that. So notice from our step 2, I have that this whole thing equals to that. So I can substitute, instead of this, I can put it that it's equal to that. A times r to the k minus 1 over r minus 1. So this equals that, and then I add plus ar to the k. Now I gotta calculate this, and I'm hoping to show that it's equal to that. So I'm gonna calculate this. So I'm gonna bring to a common denominator. So I'm going to multiply by r minus 1. So at the bottom I'm gonna have r minus 1, and at the top I'm gonna have a times r to the k minus a plus a times r to the k times r is going to give me r to the k plus 1. And then a times r to the k minus 1 is going to be minus a times r to the k. And then notice that this term cancels with that. And then if I factor out an a, I will actually factor out an a, I'll get r to the k plus 1 minus 1 over r plus 1. So this is exactly what I needed to show. Okay, so this is it. This concludes the proof. So to perform proof by induction, you have to show that the formula, the Pn is correct for Pn equals 1. And then you're going to assume that it holds for a general k. And then you're going to have to show that it holds for k plus 1. So to show that it holds for k plus 1, you're going to use this inductive step right here. You're going to use that, and then when you add it to this, you're going to perform some operations and show that it's equal to what it's supposed to be when n equals k plus 1. So this is just an introduction of mathematical induction. You're going to practice with a few examples in the homework.